Chapter 3: Information Theory, Entropy Production, and the Thermodynamics of Numeric Emergence. To fully understand the role of the zero state in numeric emergence, it is essential to analyze its properties from the perspective of information theory. Information theory, developed by Claude Shannon, provides the most rigorous language for quantifying uncertainty, information content, and structural complexity within any system of probability distributions. Here, we use the Shannon entropy functional as our central analytical tool, applying it to the probability distributions associated with numeric state configurations in our Hilbert space framework. Through this, we obtain a precise and universal measure of the information embodied within any numeric state, whether it be the perfectly symmetric zero state or any configuration that has undergone partial or complete collapse. Let us begin by introducing the general form of a numeric quantum state, denoted as psi. The state psi can be written as a superposition. For every non-negative integer n, psi is equal to the sum over n of alpha sub n times ket n. In spoken language, this means each numeric state is represented as a linear combination of all basis states, with each coefficient alpha sub n specifying the amplitude for observing the value n. The probability of observing the specific number n when measuring the state psi is given by the squared magnitude of the coefficient alpha sub n. We now define the Shannon entropy, denoted h of psi, as follows. Take the negative sum over all n of the probability, which is the squared magnitude of alpha sub n, multiplied by the base 2 logarithm of that same probability. Mathematically, this is written as h of psi equals minus the sum over n of the squared magnitude of alpha sub n times the logarithm base 2 of the squared magnitude of alpha sub n. This functional provides a direct, quantitative measure of the uncertainty or information content present in a numeric quantum state. High entropy values correspond to high uncertainty and maximal information content, meaning the state encodes a wide range of possible measurement outcomes. Low entropy corresponds to low uncertainty and low information, meaning the outcome of a measurement is nearly certain. Now, consider the case of the supersymmetric zero state. In its finite truncation up to n, the zero state is an equally weighted superposition of all basis states from 0 to n. In this symmetric configuration, every coefficient c sub n has an absolute value of 1 divided by the square root of n plus 1. Thus, the probability for any specific outcome n is 1 divided by n plus 1 for all n from 0 up to n. Substituting these values into the Shannon entropy expression, we find the entropy of the zero state equals minus the sum from n equals 0 to n of 1 over n plus 1 times the base 2 logarithm of 1 over n plus 1. This sum can be simplified. Since there are n plus 1 terms, each with the same probability, the result is just the base 2 logarithm of n plus 1. This is a crucial result. It shows that the symmetric zero state achieves the maximum possible entropy for a system of n plus 1 possible outcomes. The zero state, therefore, represents the configuration of maximal uncertainty with respect to numeric measurement. In practical terms, it is the state containing the most symmetric and complete information about the entire numeric possibility space, while displaying no preference, bias, or structure with respect to any particular numeric value. As the number of possible values, n, increases toward infinity, the entropy of the zero state diverges logarithmically. In other words, the information content of the zero state grows without bound as the numeric possibility space expands. This property fundamentally distinguishes the zero state as the information-rich origin of all numeric structures. However, the mathematical and physical significance of this maximum entropy property extends well beyond abstract information accounting. In the field of statistical mechanics and thermodynamics, maximum entropy configurations are not mere curiosities. They are the defining feature of equilibrium states. In any closed system, the configuration of maximum entropy is not only the most probable, but also the most stable and robust macrostate. All non-equilibrium configurations, when left to themselves or subjected to random perturbations, evolve toward this maximum entropy state. In our context, the supersymmetric zero state corresponds to the thermodynamic equilibrium configuration of the numeric possibility space. It is the default state toward which any arbitrary numeric distribution will naturally evolve if subjected to randomizing processes or thermal fluctuations. This analogy is not just formal. It connects the mathematics of numeric emergence with the physics of equilibrium and disorder at the most fundamental level. To make this connection explicit, we use the microcanonical ensemble interpretation from statistical mechanics. Here, each numeric eigenstate, such as ket n, represents a distinct microstate of the system. The supersymmetric zero state, which assigns equal probability to all such microstates, is thus the maximum entropy macrostate. In the language of thermodynamics, the temperature of such a configuration can be defined using the fundamental relation. Beta equals the partial derivative of entropy with respect to energy, where beta is 1 over k sub b times T, with k sub b being the Boltzmann constant and T the absolute temperature. In the idealized case of perfect symmetry, where all energy levels are equally populated, the temperature approaches infinity. This reflects a system in which all configurations are accessible and there is no energy bias, another manifestation of the principle of maximum entropy. When a measurement or collapse operation occurs, this perfect symmetry is broken. The system transitions from the maximally uncertain zero state to a more ordered configuration, a process that necessarily reduces the entropy of the system. If the collapse is complete, meaning the system is projected onto a single numeric eigenstate, such as ket n, the probability of observing n is 1, and all other probabilities are 0. Substituting this into the Shannon entropy formula, we get -1 times the base 2 logarithm of 1, which equals 0. Thus, a fully differentiated state, one that corresponds to a definite numeric outcome, has 0 entropy. The difference in entropy between the initial zero state and the final, fully differentiated state quantifies the information content that has been extracted through the process of numeric differentiation. Specifically, the entropy change delta H equals the entropy of the zero state minus the entropy of the final state, which is log base 2 of n plus 1. This is the amount of information spent or revealed in order to resolve the original maximal symmetry into an observed numeric outcome. The thermodynamic meaning of this entropy reduction is profound. The act of numeric differentiation, the process by which we obtain a specific number from the zero state, is a form of symmetry breaking. In thermodynamic language, it corresponds to the creation of order from disorder, or the emergence of structure from chaos. According to the second law of thermodynamics, any local decrease in entropy, such as the collapse from the zero state to a definite number, must be offset by an equal or greater increase in entropy elsewhere in the universe. This law imposes fundamental limits on the spontaneous emergence of numeric contrast and ensures that information extraction is always accompanied by entropy production somewhere in the total system. To generalize beyond complete collapse, we consider partial collapse processes which produce mixed states rather than pure states. We represent such a state by the density matrix ρ of lambda, defined as follows. Rho of lambda equals 1 minus lambda times the projector onto the zero state plus lambda times the sum over n of p sub n times the projector onto ket n. Here, the parameter lambda ranges from 0 to 1, controlling the degree of collapse. When lambda is 0, the state is fully symmetric. When lambda is 1, the state is fully collapsed. To quantify the information content of these mixed states, we use the von Neumann entropy, which generalizes Shannon entropy to density matrices. The von Neumann entropy of rho of lambda is defined as minus the trace of rho of lambda times the base 2 logarithm of rho of lambda. This entropy measures the uncertainty in the system, smoothly interpolating between the maximum entropy of the pure zero state and the zero entropy of a completely collapsed eigenstate. By varying lambda, we can track the dynamics of entropy production during numeric differentiation. The framework allows us to model not just the endpoints of the process, maximal symmetry and full collapse, but every intermediate state, revealing the trade-offs between symmetry preservation and information extraction that define the physics of emergence itself. In summary, the information theoretic and thermodynamic analysis of numeric states reveals the zero state to be a configuration of maximal information, maximal entropy, and maximal generative potential. The process of numeric differentiation is fundamentally a process of entropy reduction, information extraction, and symmetry breaking, subject to the universal constraints of statistical mechanics and the second law of thermodynamics. This unifies the mathematics of emergence with the physics of equilibrium and transformation, providing a single coherent language for understanding the genesis of number and the architecture of contrast in the universe.